So we will wait a few more minutes and then we will start. Stop sharing. So we are on schedule to start. Hello to all of you. My name is Agostina Serrano, and it is a great honor to welcome you all to today's webinars on behalf of Eva Jian, the leader of Win for Peace. As a proud member of Win for Peace, I am delighted to see participants eager to deepen their understanding of nuclear physics. And today's webinar, called Basics of Nuclear Physics, Review of Fundamentals, will be conducted by the esteemed Professor Nousa Benhais, former head of the Nuclear Medicine Department at the IBM Sina Teaching Hospital. We are incredibly fortunate to have her share her extensive knowledge and experience with us. I would also like to introduce Ariel Khan, who will be moderating today's seminar. Ariel is a member of Win for Peace and a recipient of the IEA scholarship at the Milbury Institute, where she's pursuing a Master of Arts in Non-Proliferation and Terrorism Studies. We are confident that today's session will be both informative and inspiring, providing valuable insights into the fundamental concepts of nuclear physics. We encourage all participants to send their questions to the webinars using the function, and our panelists will address questions at the end of the session. So thank you for joining. I hope you enjoyed the webinar. But before I give the floor to Ariel to start our session, I would like to say a few words about Win for Peace. So I will share my presentation. Can you see it okay? Yeah. So Win for Peace is an expert group established in 2023 as part of Win Global. It is dedicated to promoting global peace through the active involvement of women in crucial areas such as nuclear non-proliferation, safeguards, export control, and disarmament. It's not working, my presentation. Here. So our core mission is to contribute to world peace by coordinating initiatives across those four main domains I mentioned, with a particular focus on education and training. Our group is open to all the members of Win Global, currently boasting 24 dedicated members from 4 continents. Our group also counts on the support by the Vienna Center for Disarmament and Non-Proliferation and the UN Office of Disarmament Affairs in Vienna. We are all the members there. And in 2023, we host a series of successful webinars covering a wide range of topics. These sessions drew more than 500 registered participants for all continents, highlighting the global interest in and engagement in our initiatives. Recording of these webinars are available on the WIN Global YouTube channel for those who wish to revisit or explore these topics further. And looking ahead to 2024, we have an exciting series of webinars planned. The next one will take place in July and will focus on the current status of the Pelindaba Treaty. So Win for Peace is more than just a group. It's a movement towards a safer and more inclusive world. By fostering education, collaboration, and active participation, we aim to make a tangible impact on global peace effort. We invite all of you to join us in this journey. So thank you for your attention. And now I give the floor to Ariel. Thank you.
Thank you, Agostina. Hi, everyone. I'm very excited to be here. It's a privilege to be moderating the session for our club again. It's not a club, it's a group of experts, Win for Peace. And today I'm very honored to be introducing our guest, Professor Dr. Nusa Benrahis. So Professor served as the head of the nuclear medicine department and is now the director of the research at FMPR, Rabat University. Professor holds the highest professional degree in biophysics and nuclear medicine at FMPR as well. She also founded a nuclear medicine degree in Morocco, which recognizes by Ministry of Higher Education, and she is also one of the founding member of Nuclear Medicine Association in Morocco. This is just some of a very, very impressive background, and I'm really, really excited to be moderating the session on nuclear physics. So Professor has kindly designed this presentation and this particular lecture that is allowed and welcome everybody from all type of background, and I'm very, very excited for this webinar. So Professor, over to you. Thank you so much for joining us. Professor, you're in mute. You're on mute. There we go. No, you're mute again. You're mute again, Professor.
I am in
Yes.
mute too?
Yes,
Okay.
you're.
Okay.
Yes.
Thank you very much. I give all my thanks to Mrs. Eva Guillen, the leader of Group Expert of Win for Peace, and all my thanks to Agostina and to Ariel to help me to give this presentation. It will be a simple presentation for all levels, and I will try to ask some few basic concepts of nuclear physics. I will present a fairly succinct of what seems fundamental in nuclear physics, and if needed, I will do some exercises to consolidate the presentation. And I will share with you my presentation. So, review of some fundamental in nuclear physics. I'm not able to pass. So, review of few fundamental introduction, basic definition for atomic structure, AMU, basic definition of nuclear structure, nuclear property, nuclear forces, some words about bending energy and nuclear stability, fission and fusion, radioactivity since the history to alpha decay, beta decay, and gamma decay. I give you some fundamental quantity like Avogadro number, speed of light in vacuum, electron charge, as you know, electron and positron mass, proton and rest mass, neutron rest mass, atomic mass unit, Planck constant, and electric permittivity of vacuum and permeability and gravitation constant. Can you please remove this one? Because I am not able to remove it to have, yes, thank you. Physical quantity and unit. The System International of Units is founded on base units for several quantity, length, mass, time, electric current, temperature, amount of substance, and luminous intensity. And some the derived physical quantity are important too. Physical quantity and their unit in System International area, force, acceleration, frequency, power, electricity, electric resistance, and some radiation quantity and unit, because we are discussing today essentially for radioactivity, like exposure Kerma. Kerma is the ratio by energy transmitted by mass. It's expressed in gray. The gray is the joule per kilogram, and the dose is the absorbed energy by mass. The equivalent dose, HT, is the produce of dose absorbed by the weighting radiation weighting factor of the ray, and the dose effective is the HT multiplied by the organ or tissue radiation weighting factor. It's the equivalent dose and effective dose are expressed in sievert. Activity is expressed in international system by Becquerel, and the old unit was the Curie. We will discuss about that in the future slides. Avogadro number is a number, and this number I just want to to allow you to see all the slides. Avogadro number is a very, very big number. It's 6 multiplying by 10 to the power of 23. And for molecular mole, when we discuss about mole, when we give a mole represents n molecule, so number d'Avogadro per mole. The mass of molecular mole will be the sum of the atomic mass numbers of the constituent atom in the molecule. 1 mole of water is about 18 grams, because hydrogen is 1 gram and oxygen is 16 grams. And about CO2 is 44 grams, because carbon is 12 grams and oxygen is 16 grams. The table of Mendeleev, it's in the early 19th, the chemists had a good understanding of how to classify elements according to the periodic table. The periodic system was organized according to the number of protons in the nucleus, and currently there are about 129 elements. In the 2020 edition, this edition contains about 3,299 isotopes and 4,612 nuclides, and it's evolving. Atom history. Atom history is a very old idea. It comes from Latin atomus or from Greek atomos, where Leucippus and Democritus describe atom as the limit of the division of body. It's very, very old entity for more than 400 years before Christ, and then this date, nothing. Till the 9th century, where numerous advances in chemistry, like by the researchers like Dalton, Avogadro, and Mendeleev. And in 1895, Great leap forward Röntgen, who discovered X-ray, followed by Becquerel in 1896, who discovered radioactivity. And followed by some researchers in nuclear physics, till Thomson in 1993, Thomson developed the padding model, followed by Rutherford, 1999, who discovered the nucleus, and the first planetary model in 1911. Followed by Bohr, he builds the first quantum model, followed by Schrödinger, who developed a more elaborate quantum model. From matter to the atom, all matter is made of elements like carbon, hydrogen, etc., and so forth. the atom has been considered for a long time the smallest part of an element. Atom of different element contains different numbers of protons. The mass of an atomic is almost entirely due to the number of protons and neutrons. From the macroscopic to the macroscopic to the microscopic world, we know what means centimeter, because it's at our level, at a human scale. But we haven't idea about angstrom, about Fermi, about hundred of angstrom. It's very, very small entity. So it will be very important to know which made of the structure of matter, of atom, nucleus, and where interaction is involved, energy range, and particle and radiation. Atom size. Atom is a sphere whose diameter is on average angstrom, or a tenth of millionth of a millimeter. At the center of this sphere is the nucleus, whose diameter is of the order of Fermi, and 1 Fermi is 10 to the power minus 15 meter, or 100,000 times smaller than the atom. The ratio between the diameter of the atom and the diameter of the nucleus is about 10 to the power of 5. Schematically, if the nucleus is 1 centimeter diameter, of the diameter of the atom should be 1 kilometer. So the distance between the nucleus and the first shell of the atom is very, very big. In this example, we have helium atom with appearing in the center in pink color the atomic nucleus, and shade of gray around is the electronic cloud. The helium-4 nucleus enlarged on the right is made up of 2 protons and 2 neutrons. And this atom, like the solar system, consists only on the empty space, or free space, or vacuum. This vacuum is about 99.99%. So all the matter is the vacuum. What inside this vacuum? If it's the vacuum, perhaps the atom will collapse, and it's another debate. But if it's really the vacuum, perhaps it's the black energy or the black matter, but it's another debate. And the other important idea is radiation-like photon can pass through an atom without having any interaction, because there is a free space, a very, very big space, and a very, very, very great vacuum. So the atom consists of 2 parts: the nucleus, which contains proton and neutron, and orbiting electron around the nucleus. And the mass of proton is about 2,000 heavier than the mass of electron. The electron is theoretically a point particle. Its size is less than 10 to the power of minus 18 meter, or at least 100 million times smaller than the atom. Most of the atomic mass is concentrated in the atomic nucleus. Atom model. Since in the 20th century, since 1994, Thomson developed the first model, followed by Rutherford in 1999, followed by Bohr in 1913, followed by Sommerfeld with elliptical orbits in 1916, and finally Schrödinger in 1926. And there is a very interesting discovery of the nucleus by Rutherford experience in 1911. Rutherford, by bombarding the atom gold foil with a beam of alpha ray, he finds that alpha are repelled. Some alpha were deflected through an angle much larger than 90 degrees. The greater part of the mass of the atom was concentrated into a very small region. Atoms are almost empty, as we said, except a hard scattering center, the atomic nuclei. So we were able to calculate the radius of the atom from the nucleus to the first shell. At the distance 0 from the center of the nucleus, when the alpha particle go back, we can give this equality between Coulomb repulsion and kinetic energy of the alpha particle. So it was easy to calculate the radius of the atom. So when we compare atom model to Bohr model, atom model Rutherford in 1911, the nucleus is in the center of the atom and the electrons are around the nucleus. Neutral atom, the charge of nucleus is the opposite of charge of the electron. And Bohr elaborates in 1913, he postulates the orbits around the nucleus are circular. Energy of the electron is quantified. The electron does not radiate energy. Radiation is emitted if the electron passes from one orbit to another. It's the Bohr atom model. And in the Bohr model, this is a simple shell model with circular orbit, where n is the principal quantum number, and it represents the shell number. For for n equal 1, we have the shell k. For n equal 2, we have the L shell. N equal 3, the M. N equal 4, the N. And the radius and the energy is quantified, and the maximum of electron per shell is 2n squared. So energy and different orbital radii correspond to different energy. The total energy of the electron in the orbit ion is n equal 1 k squared and all these factors. We can see in the radius, for the radius and for the energy, they are quantified and they depend of the angular momentum. It's an integer multiple of the reduced Planck constant. There is the reduced Planck constant, and here K represents this constant. Now the K shell is constant of proportionality. It's equal 1 per 4p epsilon 0. Epsilon 0 represents the permittivity of vacuum. Schrödinger elaborated a model with shells and subshells because the model of Bohr explain Mendeleev's table lines, but not fine structure. The fine structure was developed by Schrödinger. He developed the quantum number, 4 quantum numbers to describe the possible state of the electron and gives probability of the presence of the electron around the nucleus. 4 quantum number, n represents the shell, principal quantum number. L, quantum state, quantum number of orbital angular momentum is lesser or equal to n minus 1. And ml, the number of solutions for each state, it's included between minus L and plus L, magnetic quantum number, and the spin is plus or minus half. Pauli exclusion principle, 2 electrons in the same atom cannot exist in the same state. So, Schrödinger model with shell, if we have an atom with three shell, N, K, L, and M. For n equal 1, we have L equal 0. And for n equal 2, for the L shell, we have n equal 2. So L is lesser than n minus 1, L equal 0, or L equal 1. And ML, when L equal 1, we have ML including between minus L and plus L. So the value of ML is minus 1, 1, and 0. And so forth for n equal 3. Excitation of the atom. When the atom is in the ground state, stable state, electronic configuration such as the bending energy and is maximum. When the atom underwent disturbance, it's an excited state. Disturbed atom following radioactive decay, for example, the daughter nucleus may be in an excited level. So, one electron is ejected, the electron from the K shell in this case, and the atom lost one electron is the excited state. And the gap filled and returned to the fundamental state for the atom, two possibilities. The excitation of the atom, transition of an electron from an upper orbit to the lower orbit, the energy difference between the two orbits is released as X-ray. And X-ray energy, it's equal bending energy in K minus bending energy in L. And this X-ray can also ejected another peripheric electron from the M shell or peripheral shells, and this electron is named Auger electron. AMU, how to calculate AMU? Atomic mass. Atomic mass is the mass of an atomic particle. It is expressed in atomic mass unit U. 1 U, AMU, is the 12th mass of one atom of carbon 12, and it's equal 931.5 MeV per C square. Structure and property of the nucleus. From the following table, the electron is considerably less mass than the nucleon. It is a light particle when we compare it to the proton or to the neutron. The neutron is the heaviest one, but is its mass is close to the mass of proton. Nucleus history. Einstein law of relativity in 1905. 1911, Rutherford discovered the nucleus. Chadwick in 1932 discovered the neutron. In 1934, Joliot and Irene Frederick Joliot-Curie discovered artificial radioactivity. And Fermi discovered in 1942 the divergence's first atomic pile, followed in 1945 by the first atomic bomb, and in 1960 the discovery of quarks. The nucleus. The nucleus is have a symbol here. You have a chemical symbol of the element, and we have in the upper and the left the mass number, and the mass number is the number of proton and the number of neutron, and in the bottom we have Z, left bottom, atomic number, number of proton, and the number of neutron is the difference between A and Z. Atomic number, number of proton. An atom is electrically neutral. Each of the chemical element has a unique atomic number. The energy of the nucleus is in the order of MeV, mega electron volt, or 10 to the power of 6 electron volt. We can represent also the size of the nucleus using the radius, and the radius here is 1.2 Fermi or femtometer multiplied by A to the power of third. Protons are positive charged particles 2,000 times heavier than electron, and there is their mass in the proton mass in MeV. When we compare it to the electron is a half of MeV. Neutrons are electric neutral particles with mass comparable to the proton, and it's heavier, little bit heavier than the proton. Nucleon, proton, and neutron. Nucleons are hadron particles governed by the strong interaction. Nucleons are baryon because they are made of 3 quarks. The term baryon comes from the Greek baris, meaning heavy. The proton is a baryon made up of 2 up quark and a single down quark, and its electric charge is +1. The neutron is also a baryon composed of 2 down quarks and a single up quark. Its charge is 0. Quark also have another quantum number called color charge, red, green, or blue, linked together by gluons. Gluons are particles that act as force carrier in the nucleus. Quarks colors have nothing to do with visible spectrum colors. In this depiction, we can see the 3 colors showing proton and neutron, which are composed of 3 quarks held together by the strong force. RIKEN Japanese agency researchers have measured the effect of the nucleus high density on the symmetry of vacuum. The masses of the quark only accounts for about 1% of the total mass of a proton or neutron. A significant proportion of the remainder of their mass is thought to come from the symmetry breaking of vacuum. We can classify nucleus by isotope, isobar, isoton, isomeric state. Isotope, the same Z, isotope, same Z, isobar, same A, isoton, same N. So, isotope, nuclei with same Z, but a different number of neutrons, like cobalt, here cobalt 27Z and cobalt 60 with 27 electron or proton. Nuclear refers to an atomic spatial defined by its makeup of proton, neutron, and energy state. Isotope refers to various atomic forms of a given chemical element. Isobar, the same A, like cobalt and nickel, the same A, 60. Isoton, the same, the common number of neutrons, like here helium and tritium. And isomeric metastable state is when the nucleus is in excited state and become more stable when he releases energy, gamma energy. The most example here is the molybdenum, who decays by beta minus to technetium 99M, and this metastable state decay to the stable or approximately stable technetium 9943 with gamma array 140 keV. Isotope, the same number of protons. The atoms of isotope of an element have the same number of electrons, the same chemical property, the same name. The hydrogen is the only element for which each isotope has a specific name. Hydrogen, deuterium with 1 proton and 1 neutron, and tritium with 2 protons and 1 proton and 2 neutrons. Excuse me. And here, all the other isotopes have the same name, like carbon here, carbon 20, carbon 11, carbon 13, carbon 14, or iodine, the same. The nucleus, nature would like equal number of neutrons and protons in nucleus. For Z upper than 20, Coulomb forces causes protons to repel each other, requiring more nuclear glue to hold the nucleus together, adding more neutrons. Stable nuclei can be found for all elements up to Z equal 83. Above Z equal 83, all non-nuclei are unstable or radioactive. Radionuclei, there are stable and unstable elements in nature. The nuclei of unstable element transform naturally, they constitute natural radionuclide. Nuclear reaction in atomic centers produce artificial radionuclide more than 2,500. Number of stable and radioactive natural nuclei present on the Earth is about 338 with 288 primordial nucleides containing 256 stable isotopes and 32 long-lived, half-lived, longer than 100 million years. In all, we have natural radionuclide about 86 and stable nuclide about 256. This depiction is very, very interesting because we can be aware about the vacuum in the atom, or in the matter. If the proton and neutron in this picture were 10 centimeters across, then the quarks and electron would be less than 0.1 millimeter in size, and the entire atom would be about 10 kilometers across. So the same idea, there is the big vacuum, and the vacuity in the atom is very, very important. Scale and objective. Nuclear scale is in the order of Fermi or femtometer, too small for direct investigation. We need to answer what are the building blocks of a nucleus? First question. Second question, how do they move relative to each other? And the third question, what laws governing them? We need to understand nuclear force, nuclear structure. We also need high energy physics. If we look to the lead 207, this lead has 82 protons in the nucleus. Why doesn't the lead nucleus burst apart? We have 5 responses. Coulomb repulsive force doesn't act inside the nucleus. Gravity overpowers the Coulomb repulsive force inside the nucleus. The third is the negatively charged neutron balance the positively charged proton. Protons lose their positive charge inside the nucleus or none of the above. The right response is none of the above. Why? For that, we can develop a little bit the bending energy and nuclear forces. The force that binds the nucleons together is called the strong nuclear force. It's a very strong but short-range force. It's essentially zero if the nucleons are more than about 1 Fermi apart. The Coulomb force is large. This is why extra neurons are needed for stability in high Z nuclei. Nucleus interaction. The nucleon-nucleon interaction is still unknown nowadays, but we try to explain some interaction inside the nucleus by Coulomb interaction, by strong nuclear interaction and weak nuclear interaction. Coulomb interaction is a repulsion force between protons, strong nuclear interaction forces of attraction between all nucleons, very intensive at short distance, and weak nuclear interaction is the transformation neutron to proton. The strong force can explain how can protons be held tightly together in the nucleus if like charges repel. The strong force is a type of force that causes the proton in the nucleus to not repel each other. The strong force is usually 100 times stronger than the electromagnetic force that repels the positively charged proton from one another. The only limitation of the strong force is that it's a short-range force, and to work, the proton and neutron have to be very close together. That quickly becomes extremely weak as proton and neutron get farther apart. When protons are separated by distance, the electric force takes over and causes like charge to repel. Under certain circumstances, the repelling electromagnetic force becomes stronger than the nuclear force. In this case, the nucleus splits and leaves behind the different elements. This is a form of nuclear decay. Fundamental forces in nature: strong force, electromagnetic force, the weak force, and the force of gravity. The relative strengths, the gravitational is relative the weakest one when we compare it to the strong force, followed the strong force, the strong nuclear force is followed by the electromagnetic force is 100th lesser than the strong nuclear force, and followed by the weak nuclear force, so is millions lesser than the strong force. Fundamental force origin: just after the Big Bang, the 4 forces were merged into a single force known as the united force. As the early universe expanded and cooled from its original temperature at this time, and at this temperature, it underwent a type of phase of transition in which the gravitational force took a separate identity. After that period, it's very, very quick period after the Big Bang, emerged the Grand Unified Theory. And in this time, at this temperature, we can see the strong force become separate, a separate force, followed, and similarly, the weak force become the weak force become separate at this to the power minus 10 second and 10 to the power 15 to the power 15 degree Kelvin. The weak nuclear force measured too become separate, and the electromagnetic force too. What is the ratio between Z and A for a nucleus? For element, the ratio Z per A is about 0.4 to 0.5, with a notable exception for hydrogen, for which Z per A equal 1. The ratio Z per A gradually decreases with increasing Z, about 0.5 for low Z element, and about 0.4 for high Z element. Bending energy and nuclear force. The total mass of a stable nucleus is always less than the sum of the masses of its separate proton and neutron. Where has the mass gone? It has become energy E equal mc square. Nucleus mass is lesser than the sum of the masses of its constituent, as we see in this picture. So bending energy equal the difference in mass multiplied by c square. The difference between the total mass of the constituent and the mass of the nucleus is called the total bending energy of the nucleus. The bending energy is the energy needed to break a nucleus into individual nucleus. And the energy bending is the total mass of nucleon minus mass of the nucleus multiplied by c squared. Bending energy per nucleon. To compare how tightly bound different nuclei are, we divide the bending energy by A to get the bending energy per nucleon. And as we see in this scheme, we have bending energy per nucleon varies with A. It's about 8 MeV per nucleon, and rise rapidly with small a, it rise rapidly, brought the maximum at 8.7 MeV per nucleon at A equal 60. 8 equals 60. Gradual decrease at large A. Larger value implies atom more stable, the higher bending energy per nucleon correspond to the more stable nucleus, and the most stable nuclei have A equal 60, like iron, cobalt 60, and nickel 60. This scheme suggests two methods for mass to energy conversion to allow us to understand what is fusion and what fission. Nuclear fusion and fission. Fusion of low A energy, low A nuclei, A nuclei, creates a more massive nucleus, release energy. For a long time, it was considered not successful in net energy generation, remains active field of research. Since August 8, 2023, US scientists working at the Lawrence Livermore National Laboratory have achieved net energy gain in nuclear fusion for a second time. So we can have electricity made using fusion technology in about 2028. And we have, in the right side, we have an example of fusion. Fusion of deuterium, tritium with helium, product are helium, energy, and neutron. Fission of a large nuclei, bombardment of large elements like uranium-235 by thermal neutron will create two more stable nuclei with lower mass. Process transforms some mass into kinetic energy. Fission reactors are important means of production of electric power. Radioactivity. When the strong force is not great enough to hold the nucleus together, nucleus can means to give of matter and energy. The process of nuclear decay is called radioactivity. Process of nuclear decay, all nuclei that contain more than 83 protons are radioactive. Almost all elements with more than 92 proton does not naturally on Earth. They have been produced only in laboratory. We have here a scheme of nuclear transformation and decay scheme. When the atomic nucleus undergoes the spontaneous transformation called radioactive decay, radiation is emitted like alpha decay, beta minus, beta plus, electron capture, and isomeric transformation. Radioactive ray were observed to be of 3 types: alpha ray, beta ray, and gamma ray. History of radioactivity, as we said in the previous slides, Henri Becquerel discovered radioactivity in 1896 and received, he shares the half of Nobel Prize with Pierre and Marie Curie when he discovered that uranyl sulfate impresses photographic plate, followed by Pierre and Marie Curie in 1898. They received 2 Nobel Prizes, the first one in physics and the second one in chemistry. And Irene and Frédéric Joliot-Curie discovered artificial radioactivity and received the Nobel Prize in 1935. Tribute to Marie Sklodowska-Curie. Even much of today's nuclear science is based on her work and her husband's work. She received 2 prizes, 2 Nobel Prizes, and even with deteriorating health, when she discovered highly radioactive polonium and radium, and all her works in polonium and radium are responsible of deteriorating health, the Curie continued their research. Much of today's nuclear science is based on their work. Rays of Hope. This sentence was said for the first time by Pierre Curie on June 6, 1995 at the Swedish Academy of Science in Stockholm. He said, "I am one of those who think with Nobel that humanity will derive more good than harm from new discovery." Followed by Atoms for Peace. Atom for Peace is the USS President Eisenhower bet in 1953 in his speech delivered on December 8, 1953 to the United Nations General Assembly. 4 years later, in July 1957, the International Atomic Energy IAEA was created, based in Vienna. This organization mission is to ensure the safe, sustainable development of nuclear science and technology in the fields of energy, environment, health, and agriculture. Isotope and radioactivity. Most of the isotopes which occur naturally are stable. A few naturally occurring isotopes and all of the man-made isotopes are unstable. Unstable isotope can become stable by releasing different types of particles and energy. This process is called radioactive decay. And here in this slide, we can see the valley of stability where nuclei with excess nuclei move down to the valley towards stability. And we have the nuclide chart. We have the line proton equal neutron. And for the light element, the light element have all of them have n equal z, the number of protons equal the number of neutrons. And in this side, neutron deficient nuclide with decay by beta plus and electron capture, and on this side, neutron excess nuclide with decay by beta minus. In this stability, the diagram of stability is the same as the previous one, and we have 3 areas: beta minus when we have excess in neutron, beta plus and capture electron when in the area 2 when we have excess in proton, and here when we have excess on proton and neutron, we have alpha and fission. And we can see in this diagram, the isotopes are all aligned parallel to the y-axis. And we have isotopes are all the parallel with the same n parallel to the x-axis. Nuclear radiation, 3 types of nuclear radiation emitted. We can discuss about alpha particle, beta particle, and gamma ray. Radiation, the process of emitting energy in the form of waves or particles. Where does the radiation come from? Radiation is generally produced when particles interact or decay. A large contribution of the radiation on Earth is from the cosmic sun or from terrestrial radioactive isotope. A terrestrial radioactive isotope like potassium-40, rubidium-87, or the 3 uranium. The 3 uranium decay to the radon 222, and this radon is responsible for 90% of the health effect. How we have tritium and carbon-14 coming from the cosmic ray? Yes, when tritium and carbon are formed by neutrons coming from the cosmic rays acting on nitrogen. When they come, the neutron comes from cosmic area. When they are penetrating in the high atmosphere, they interact with nitrogen 14, and we have tritium, and we have here carbon-14. Carbon-14 is oxidized to be CO2, and CO2 by photosynthesis is incorporated in plants and animal, and from plants and animal to human. They are responsible of environmental radioactivity. Radiation is going through you at this very moment. Rate of decay. Rate of decay, how frequently one of the atoms emits this radiation. A very important point here is that we cannot predict when a particular entity will decay. Some radioactive substances have a very high rate of decay, while others have a very low decay rate. To differentiate different radioactive substances, we look to quantify decay rate. The rate of decay, nuclear decay is a random process. The decay of any nucleus is not influenced by the decay of any other. The number of decay in a short time, like delta T or dt interval, is proportional to the number of nuclei present to the time. Here, lambda n equal minus lambda n then lambda t or dt. Lambda is a constant characteristic of that particular nuclide called the decay constant. Decay constant or probability per unit time that the nucleus will decay. Rate of decay, if we have n nucleus at time t, if we have dn nucleus between t and t plus dt, we have dn equal moins lambda n dt, so we can write dn per dt plus lambda equals 0. dn per n equal moins lambda dt. If we integrate this equality, we can find integral dn per n is like integral dx per x is ln the n. And integral on lambda is constant is moins lambda t. At t equals 0, we have n0 constant, so ln the n equal moins lambda t plus ln 0. We can write that ln n per n0, because ln n minus ln n0 equal ln n per n0 equal moins lambda t, and we can, if we this equality, if we give exponential to this equality, we can have n per n0 equal exponential minus lambda t. The number of nuclei decrease exponentially with time. Activity. The number of radioactive parent nuclei as a function of time, assuming as lambda p is constant, is n de pt equal np0 exponential moins lambda p, and activity is lambda multiplied by np, p design parent, the radioactive parent, and it's equal lambda p n0 exponential moins lambda pt. The system intersection is the Becquerel, which is defined as 1 disintegration per second, 1 dps. old and classic unities Curie, 1 millicurie equal 37 megabecquerel, or 1 Curie equal 37 gigabecquerel, billion becquerel. So active 1 Curie represents the activity of 1 gram of radium-226. Decay of radioactive parent into a stable or unstable daughter. Decay of radioactive parent into stable daughter D with decay with lambda P. We can put that the rate of depletion AP is dNP per dt. It's equal minus APT moins lambda P TP. Fundamental differential equation for this equality can be rewritten in integral form. And in the end, we have NDP and dNPT bar NPT since 0 to time equal t is minus integral of lambda P dt. Half-life and rate of decay. This equation can be solved using calculus for n as a function of time. N equal n0 exponential moins lambda minus lambda t. The half-life is the time it takes for half the nuclei in a given sample to decay. And at this moment, the time is equal ln2 per lambda equal 0.693 per lambda. We have N0. It is the half-life when we have N0 per 2. Other interesting things to know. We defined the half-life, the time required for half of a sample of radioactive substance to decay. We have NT bar N0 equal 1/2. So we have NT equal N0 per 2. So we can write 1/2 equal exponential minus lambda t. So we can write 2 equal exponential lambda t, and ln the 2 equal lambda t. So ln the 2 equals 0.693. It's a time. It's expressed in second. One half-life corresponds to N0 per 2. Two half-life correspond to N0 divided by 2 squared. 3 half-life correspond to N0 divided by 2 to the power of 3. And when we can say at 10 period, we have N0 divided by 2 to the power of 10. And if each NT or N half-life, the N0, the initial nucleus, decreases to the N0 divided by 2 to the power of N. For half-life, the number of nuclei decreases by 2 to the power of 10. It's about 1,000. So about 10 half-life, we have only 1,000 from the first nuclei, because to the power of 10 it's equal 1024, it's about 1,000. So we can calculate residual activity. Calculation of residual activity, A0 initial activity, T integer number of T. At 1 period, the residual activity is A0 per 2. At 2 half-life, we have A0 divided by 2 square. At 3 half-life, we have A0 divided by 2 to the power of 3. And in the same calculation, we can say at 10 half-life, we have only the thousandths of the A0. The residual activity is reduced to the thousand after 10 half-life. Half-life is the time it takes for half of the atom of a radioactive substance to decay. For example, suppose we had 20,000 atoms of a radioactive substance. In the half-life, if the half-life is 1 hour, how many atoms of that substance will be left after? After in 1 period, we have the half, 10,000, and we have only 50% of atom remaining. After 2 hours, 2 lifetimes, we have 5,000. And here the same, we have N0 equal 100%. After one period, we have 50%. After two half-lives, we have 25%. And after three half-life, we have only 12.5%. Mean average of tau. Can you reduce that? No. Can you reduce that, please? Mean average life tau is a of a radioactive parent is the time during which the number NP or radioactive nuclei or its activity falls to 1 per A, about 37% of NP0 or AP0. So we can write that for activity and number of nuclei. And that means what? That means that we have exponential -1 equal exponential minus lambda p 2p. So the alone possibility is to have 2p, the mean life 2p equal is the reverse of lambda p. It's the reverse of lambda p. It's a time that is expressed on second, and 2p is 1.44 multiplied by the half-life. The lifetime of particle is an alternative, an alternate definition of the rate decay. It's just another way of expressing how fast the substance decay. It is simply, it's 1.44 multiplied by half-life. The lifetime of a free neutron is about 14.7 minutes. The number remaining after some time is given by the radioactive decay law, and E equal 2.718. Activity, can you please reduce this one? You have the activity. The lifetime of a free neutron is about 14.7 minutes. After one lifetime, we have about 37%. After two lifetime, we have 13.5%. After three lifetime, we have 0.05 fraction of remaining neutrons. So after, as we saw in this diagram, after 4 to 5 lifetime, almost of all of the unstable particles have decayed all. Some example of radioactive product, we have uranium, 4.5 billion years, and we have here polonium 214 is about 1.5, 10 minus 10 to the power minus 4 seconds. So very, very short to very, very long. And here we have a half-life and lambda for some radioactive product using in nuclear medicine. And in this table in the bottom, you can see if you have 1 million of nucleus in the beginning, after 10 period, we have only the thousands, we have only the 1,000 nuclei. And about 10 others half-life, we have only 1. Activity, we have here the activity plotted against time. T for a simple decay of a radioactive parent P to stable or unstable daughter. We have the equation we established in the previous slides, APT equal AP0 exponential minus lambda PT. And this curve illustrates the concept of half-life. We have AP0 dividing by 2. The concept of 2P, we have 2P correspond to AP0 divided by A, and exponential decay, area under the curve from T equals 0 to T equal infinity is represented in gray here, and this area is the integral of APT. It's the integral of AP0 exponential minus lambda PT, and this integral is the integral of AP0 is constant, so it's the integral of minus lambda pt from 0 to infinity, and the integral of exponential lambda pt is equal 1 per lambda. So the reverse of lambda pt, or the reverse of lambda, is 2p, as we defined it. So area under the curve is apt 2p. The slope of tangent, we have the tangent here. The slope of tangent is, the tangent is apt equal minus lambda p ap0 t plus ap0. So the slope is equal lambda p ap0. It's like ax plus b, and a is represented by lambda p ap0. And the x-axis intercept t at time equal 2p. Yes, when we have ap0 equal 0, when we have time equal 0 here, we have 0 equal 1 lambda p ap0 t plus ap0, and we can factoring ap0 equal ap0 factoring 1 minus lambda pt equal 0. So t must be equal to the reverse of lambda p, and the reverse of lambda p is equal to p. So the intercepts the x-axis in the 2p. When we have decay of radioactive parent into stable and unstable daughter D, which in turn decay into granddaughter G, P to D and D to granddaughter G, rate of change dNpt dt in the number of daughter nuclei D equal to the supply of new daughter, because P is decreasing to give D, nucleotide decay of P given as lambda P and the P, and the daughter is unstable, so it decays to the granddaughter, and the loss of daughter nuclei D from the decay of D to G given as minus lambda D and the D. So we can write the and the D T by Tt is equal to the lambda P and Pt minus lambda D and the dt. So the number of nuclei, just to give integral at this equality, and we have n to d equal this this equation. And to have activity, we have n to d. If we multiply n to d by lambda d, we have activity of d. And this activity of d, we can in P0 lambda p lambda d. And it's equal, if we are factoring lambda d, we can have, we divide by lambda d here and here. And if we we are factoring exponential minus lambda p, we can have this equation too. So daughter activity at d versus time is when the parent is decreased in this curve. It's easier to interpret in this diagram. The daughter is rising, pass by maximum and decreasing to be stable or to give another granddaughter. Daughter activity initially rises with time, reach maximum at characteristic time, and the maximum, what represents the maximum? It's just a mathematical calculation. The maximum of the curve corresponds to the cancellation of the derivative function, and the second derivative is strictly negative because we have a maximum. Or it's the intersection between apt and addt. Mode of disintegration: neutron-rich nuclide have excess number of neutron. Proton-rich nuclide have excess number of proton. Decays slight proton-neutron imbalance, proton into a neutron in beta plus decay, neutron into a proton in beta minus decay, large proton-neutron imbalance, alpha particle in alpha decay, or proton in proton emission decay, neutron in neutron emission decay, and for very, very large nuclide A upper than 230, we have spontaneous fission competing with alpha decay. And we can use and we can discuss, if we have time, only about the third first. And in each nuclear transformation, a number of physical quantity must be conserved. It's fundamental. The most important conserved physical quantity are total energy, momentum, charge, atomic number, and atomic mass. Nuclear transformation are usually accompanied by emission of energetic particles, charged particle, neutral particle, photon, neutrino, and here we have radioactive decay and emitted particle respectively for each radioactive decay. When the mode of decay, can you kindly remove this because to allow the mode of radioactive decay, total energy of particle released by the transformation process is equal to the net decrease in the rest energy of the neutral atom from parent P to daughter D. Decay energy Q value is given as Q equal the mass of parent minus the mass of the daughter and the particle emitted, multiplying all by 6 squared. MP, MD, and M are the nuclear rest mass of the parent, daughter, and emitted particle respectively. And they are expressed in unified atomic mass unit U. Radioactive decay energetically possible if Q is positive. Energy equivalent of Q is shared as kinetic energy between emitted particle, the daughter, and the daughter products. But if the daughter is very, very heavy, it's shared between just the light particle, as we can see in beta emission. Transmutation is the process of changing one element to another. We have give example of polonium 210 gives an alpha particle. It will become the lead 206. When alpha radiation occurs, an alpha particle is emitted from decay nucleus. An alpha particle is made of 2 protons and 2 neutrons bound together, charge plus 2 as it has 2 protons, atomic mass is equal 4. An alpha particle is the same as helium atom without electron. In general, alpha decay can be written NaZ becomes the daughter is N prime, A minus 4, Z minus 2, and helium nucleus. Alpha decay occurs when the strong nuclear force cannot hold a large nucleus together. The mass of the parent nucleus is greater than the sum of the masses of the daughter nucleus and the alpha particle. This difference is called the disintegration energy. Here you have an example of radium to decay to radon 222 and alpha. Alpha decay is a nuclear transformation which energetic particle helium is emitted. Atomic numbers are decreased by 2. Atomic mass decreased by 4. Naturally occurring as kinetic energy is about 4 to 9 MeV. It's very, very energetic. The range in air is 1 to 10 centimeters, and the range in tissue is very reduced. It's from 10 to 100 micrometers. For this particularity, it's the alpha element are very useful to treat tumors because they have they can deliver very big energy in very small area, about few micrometers. Example, we have polonium who decrease to give lead 206, and we calculate here energy, and the difference in atomic mass unit is about 0.0058, and energy units we multiply by 931.5 MeV, and it's about 5.4 MeV. It's very important, as we said, it's about 4 to 9 MeV. Compared to beta particle and gamma radiation, alpha particles are much more massive because we have 2 protons and 2 neutrons. So 1 proton is 2,000 heavier than 1 electron. So 1 alpha particle is about 8,000 heavier than an electron. So alpha particle also have the most electric charge, +2 compared to -1 in the the beta particle, and no charge for gamma radiation. Example of radium to radon and helium. Beta decay. Beta particle is a fast-moving electron which is emitted from the nucleus of an atom undergoing radioactive decay. Beta decay occurs when a neutron changes into a proton and an electron. The atom now has 1 more proton, so it becomes the element with an atomic number 1 greater than that of the original element. Since the neutron decays into a proton, the total number of protons and neutrons doesn't change during beta transmutation, so the atomic mass number stays the same. We call that isobaric transformation because the A is not changed. Transmutation in beta radiation, cesium 137 to become 55 to become barium 137 56 for the number of protons, and an electron is ejected. Sometimes the electron emitted from the nucleus during beta decay is caused by the weak force. Beta particle, the mass is very light, 0.0005 U. The symbol is beta, as the charge is -1. Beta particle, we have parent decay to daughter, electron, and energy. And this equation seems to violate the established energy mass conserved laws. As we said in the previous slides, it's very important to don't violate these laws. When accurate measurement of beta decay were made, it became apparent that energy, angular momentum, and linear momentum were not accounted for by the daughter nucleus and electron alone. Either a previously unsuspected particle was carrying them away, or 3 conservation laws were being violated. This is explained by the simultaneous emission of a single and vanishingly small mass called a neutrino. The neutrino was discovered through analysis of energy and momentum conservation. Neutrino, Wolfgang Pauli made a formal proposal for the existence of neutrino by conservation of light in 1930. Enrico Fermi gave neutrinos their name, meaning little neutral ones. Frederick Renz and Clyde Cowan in 1956, so 26 years later, announced the first evidence of the existence of neutrino. Neutrino is an uncharged elementary particle that is believed to be massless or to have a very small mass. There are 3 forms we discuss here about electron neutrino, but we can find muon neutrino and tau neutrino. Neutrino is lepton, like electron, light elementary particle. The name lepton comes from Greek and means light, which does not undergo strong interaction opposite to hadron. There are 6 kinds of lepton, electron, muon, and tau, and electron, muon, and tau neutrino. Beta minus decay, we have neutron-rich parent nucleus, transform neutrino into proton and an antineutrino. The parent decays to the daughter with the same A, so they are isobar, electron and antineutrino. Example, cobalt-60 to became nickel with electron and antineutrino. If we want to calculate the energy of demonstration of the energy of beta minus, X as Z becomes X prime Z plus 1 electron plus antineutrino. For calculating the energy, is the initial state minus the final state. The initial state is the mass of the nucleus AZ minus the mass of nucleus AZ plus 1 plus the mass of electron and the mass of antineutrino. The mass of the nucleus AZ is the mass of the atom AZ minus Z fois Z mass of electron. The mass of nucleus AZ plus 1 is the mass of AZ plus and minus Z plus and mass of electron. The mass of antineutrino is about 0 because the neutrino electron mass is lesser than 1.1 eV by c squared. So Q beta minus equal the difference by atomic mass from the parent minus the daughter, c squared. Beta emission is possible if Q beta plus is positive, delta M c squared is positive, so delta M must be positive. Since the nucleus is massive compared to the beta particle and the neutrino, almost all the energy will show up as kinetic energy in the beta and neutrino. Q beta minus once released, so is shared between electron and antineutrino. If it does not carry energy, if it's the beta particle electron which takes away all the energy, so the maximum of energy of the electron equal delta M c squared. Energy of spectrum is continuous spectrum. So if we compare alpha and beta particle, we can say that beta particles are much faster because they are very, very light particle and more penetrating than alpha. Alpha particle can be stopped by a paper, but beta particle will be stopped by a sheet of aluminum foil or plastic. Beta plus, proton-rich parent nucleus in proton. Proton becomes neutron and positron is an antiparticle and neutrino. The daughter is isobaric transformation 2. Beta plus efficient proton excess proton-rich parent nucleus to become more stable converts proton to neutron. X as Z transforms to X prime A Z minus 1 plus positron plus neutrino, and the nuclear equation is this. The result emission, beta positron is an antiparticle and neutrino, and we can do the same calculation to have the energy, and the beta plus is possible if it's positive, and to be positive, a beta plus can be delta M c squared must be higher than 1.022 mega electron volt. So the maximum energy of the beta plus particle is delta M c squared minus 1.022 MeV. 1022 MeV is the energy of the positron and electron. Secondary phenomena of this beta plus particle. These positrons propagate through matter, losing their energy. Unstable when they are at rest. They encounter electron. There is annihilation and disappearance. We have positron. The matter is rich in electron. The positron is an antiparticle, but with electron when positron when they meet the electron, it become energy, disappear of matter and apparition of we find energy. This emission of 2 gamma photons of the same energy h nu, 0.511 MeV for each one, emitted in opposite direction. Radionuclide undergoing beta plus decay, often called positron emitter, used in nuclear medicine for PET functional imaging. Most common PET tracer is fluorodesoxyglucose in oncology and in several medical indications labeled with fluorine 18. It's the best example if used in nuclear medicine and position PET-CT, positron emission tomography. Electron capture, it's a competition between beta plus and capture of electron. Capture electron is favored if the energy is lesser than 1.022 MeV. The beta plus is not possible, and the decay is with electron capture. Excess of proton, nuclei with an excess of proton can be transformed by capturing an electron, generally from the most center K shell, otherwise, and to a lesser degree to L shell, and to give neutron and neutrino. The equation is the XAZ plus electron gives daughter X prime AZ minus 1 plus neutrino. It's isobaric transformation too. Electron capture is a nuclear transformation in which nucleus capture an aptotomic orbital electron. Example of electron capture, iodine capturing electron and becoming tellure and neutrino. Tellure is in excited state of tellure, the stable, the ground stable nucleus, decay to stable or to ground state by gamma decay. For this transformation to occur, it's necessary that the difference in energy between the initial and final state be greater than the bending energy EL of the electron in the K shell, delta MC square upper than bending energy. So the energy of capture electron is the delta MC square between the parent and the atomic mass and the daughter must be upper than the bending energy in the K shell. After alpha, beta, or beta plus or capture electronic, the daughter nucleus is in excited state, so electromagnetic excitation of nuclei, excitation by gamma, by internal convection, or by materialization by E plus and electron to be more stable. Full amount of decay energy available not expanded will reach ground excited state by gamma emission, one or more gamma, internal conversion, transfer of excitation energy to atomic or orbital electron, vacancy in shell filled by higher orbital electron, resulting in characteristic X-ray and or Auger electron. And finally, if the nucleus is has a very big energy, higher than 1.022 MeV, we have creation of internal pair or materialization. Gamma decay are not charged particles like particle alpha and beta. Gamma rays are electromagnetic radiation with high frequency and wavelength, energy equal H nu equal Hc per lambda. Gamma ray photons that are emitted when an excited nucleus moves from one energy level to a lower energy level. X-ray photons that are emitted from the atom when atomic electron move from one energy level to lower energy level. And we have here the same. We have an example of, yes, when the excitation of the nucleus is instantaneous, it's between 1 microsecond to 1 second, and when the time is upper than 1 second, is a metastable state. So gamma ray, the gamma ray is the alpha needs a paper, the beta a plastic, but gamma ray is very penetrating. They need leads or concrete. They are no mass or no charge, but travel at speed light. It takes concrete or lead to stop the penetration, but they are far less damaging to living tissue than alpha or beta. Donc,
Professor?
as you see, we think as a physicist, but we work as a physician. Thank you for your attention. Yes, yes, Ariel. Ariel?
Hi, thank you. Yes, I'm here. Thank you so much for your presentation and lecture is really insightful and very helpful. Unfortunately, we run out of time for Q&A, but I don't see any wait. So thank you so much, Professor, for joining us. We'd be grateful for your time and your presence is really appreciated. Over to you, Agostina.
Yes, thank you, Ariel. And as we came to the end of today's enlightening webinar, I would like to extend our gratitude and on behalf of Eva to Professor Nosa for sharing her invaluable knowledge and expertise with us. Her insight into the fundamentals of nuclear physics have truly enriched our understanding. I hope you all enjoy it. And a special thanks also goes to Ariel for her excellent moderation. We appreciate the participation of everyone who joined us today. And remember that we will have the webinar on YouTube. And I'm pleased to invite you to our next webinar, which will take place on July 12th. The session will focus on Pelindaba Treaty, an important topic in the field of nuclear non-proliferation. So we look forward to your participation. And thank you once again. We hope to see you at our upcoming event. And thank you, Professor. Do you want to say something?
Thank you so much, Agostina, for your kind words. And thank you to Ariel. And my presentation in 1 hour is too long. And I hope that the audience and participants understand what I try to give them as a take-home message. Yes.
Thank you. And for sure, we can organize the second part. So thank you very much.
Thank you. Thank you so much.
Bye.
Bye.